Welcome back. We're talking about section 3.5, which is the symbolic argument section. So just the last section we're going to do this chapter 3, building on what we've talked about in the previous. We talked about what would be a sensible way of saying what makes a good argument or a good statement, a true statement, the way that you say it. Does it make sense, I guess, sort of thing. So building off what we've been doing, we're going to add on to it a little bit. So follow along in your notes with me. If you haven't already, get those notes ready or pull them up online. But so the first one we're going to study is called the law of detachment. This is one of our symbolic arguments. Oh, and by the way, let me back up to what the notes say here before I get ahead of myself. It says a symbolic argument is valid. We'll call it valid. And it's valid only if the final statement in the truth table, in that final column statement, we talk about the final answer, if that final column has all truths in it. It has to be a tautology. You know, everything has to be a T for it to be a valid argument that's just always true. This is just an okay way to say it. It always works that way. So an argument is not valid if there's any one F in the list. You throw it out and say that would not be a valid argument. So that's how we can prove it, I guess, if we have to, and we'll start out that way. But then we have some shortcuts, some that are listed as here's some good arguments that always work. All right, so the first one we're going to talk about is called the law of detachment. And this is a valid argument. This is one of our go-to ones that, and you may say when you listen to this, like, I don't know, this is just obviously this is a valid argument, but still it helps us kind of get the idea of what we're doing here. So just, go with me here. All right, so if we have the statement, premise 1, if John Mellencamp sings the national anthem, then U2 is going to play at halftime. So if I said to you, hey, if John Mellencamp sings our national anthem, then U2 is going to play. Well, if John Mellencamp gets up and sings the national anthem, then you expect that U2 is going to play at halftime. So that kind of makes sense, right? But let's just still use our argument, our symbolic language to show the argument is valid and why. All right, so we would say this first sentence I said, premise 1, if John Mellencamp sings the national anthem, then U2 will play at halftime. Let's call that my first sentence. Then the second sentence is John Mellencamp sings the national anthem. So then you should be able to assume the conclusion, we would call it, almost like it's a plus sign, this plus this would equal or conclude that U2 would play at halftime. Symbolically, we could say this first premise was a conditional, if P then Q. If John Mellencamp sings the national anthem, then, so our conditional, U2 plays at halftime, we'll call that statement or symbolically Q. Then we would say plus, it's almost like we're doing a little math problem, plus premise 2, John Mellencamp sings the national anthem. So I'll say P happened, all right? And that's all there is to it. There's not an if then, it's just P happened. John Mellencamp sings the national anthem, P. Therefore, or we can conclude these 3 little dots in math class, that's a symbol for therefore, or it leads to this natural conclusion that Q is going to happen. Q was the second part, U2 will play at halftime. So if P then Q plus P happened, therefore we can conclude Q. That would be the symbolic argument for what was just stated here. Again, that's called the law of detachment or modus ponens. And there's some Latin terms for some of this logic you'll see along if you're reading in the book as well. Now, this just so happens to be one that's stamped into your book section and said, this is always true. That just makes sense. That's a valid argument. But sometimes some will come along and it'll say, is this valid or invalid? And we won't have one already ready-made maybe on our list. Like I've been telling you, kind of keep a list of equivalent statements. Same thing here with valid arguments. Maybe keep a running list of some that you find to be valid arguments. We'll have a little list in our book of some to get us started. This is the first one. We'll make a nice little list in a minute, though, to wrap it up at the end. But, okay, so let's just say we don't know this is in the book. We don't know the answer that it's already valid, and we're not trying to really reason it out. Let's just do it to prove it. How would we show that? So what we had was the idea if P then Q, and then P happened, therefore Q. So how would we do that to prove it? Those truth tables. Still working on the truth tables here in this section, just a little bit. You won't have to prove all of these, but I want you to be able to if needed. So there's a P and a Q, so just 2 things, 2 statements, 2 ideas. That John Mellencamp idea and the U2 idea. There was only 2 things going on. So that's just the 4 cases for a truth table. Either both of those are true, true, false, false, true, or both false. 4 possibilities, 4 cases. So the way we prove this is we do it like a little math problem. This plus this leads to that. So the way that you prove it, you write it like a little math problem. Our plus sign is our and sign, and then our leads to is our arrow sign. So we would write this as, P, let me write it on the line, but we're going to do the truth table. If P then Q, and we'll put that in parentheses for our plus problem here, plus, or that and sign, P, we'll do all of that, get the answer to that, and then the last part will be the conditional. Therefore is the conditional, if this, then Q. So that's how you write it out to prove it. All right, so we can do truth tables now. We've been having to fight this battle all through the section, all through the chapter, right? So we can do this step at a time. It's a messy one, but let's hit it. So again, you do this plus this, and then all that goes in a parenthesis. You're going to do the answer to this part and see if it's the same. You're going to compare it with a conditional to the conclusion Q. All right, so doing parentheses first. The innermost parenthesis is this if P then Q. I'm not going to copy these over. I'm just going to look. The if P then Q rule, T to T is T. T to F is the F. That's the one where they broke the promise. A T to F is F. All the others are true. So that's the answer to that parenthesis. I am going to copy down column P. It's T, T, F, F. And then I'm going to do the AND rule, right? That'll be the final answer inside this parenthesis. The AND rule says it takes 2 T's to be a T. So that's all just this. This is the answer to all of this, the total this plus this. Then I'm going to do the conditional rule, if P then Q, so that the conditional rule, comparing this with column Q. I think I will write this down just to have it to look at easier. So here to here, and then my final answer, I'm going to put right down this column. So comparing the answer to the parenthesis with Q. Remember the conditional rule is if you have a true to a false, that's when you break the promise. So T to T is fine, F to F is fine, F to T is even fine, and F to F is fine. Those are all trues. There was no T to F. So all true. That's what we call a tautology. Whenever the final answer to it's all true, it's called a tautology, or in this case even an implication because it was a conditional. But anyway, it's valid. That would be proving that to be a valid argument. All right, so that's how we prove it. On the next page, I have that listed in from your book, the steps to solve this type of problem. Number 1. Try to write your argument in symbolic form. Change it to P, Q, and sometimes you have a third part, an R, so however many statements you have. Then make your truth table out for how many variables you're going to have. Then compare the form of the argument. You might write that down and say, it's going to be on this list I'm going to give you in a minute, a list of valid arguments and a list of things that are always invalid. And you might even be, keeping your own running list too. So this is definitely on the valid list. We've proved this is a valid argument. And it even has a name. All right, but if you do not find it on your list and you have not already proved it and you have to figure that out, then you go to step 3. If the argument contains 2 premises, you write it as a plus. In our language here, a plus is the conjunction sign or the caret sign, the inverted V. So this plus this, put all that in a parenthesis and do it in the order of operation. And then say arrow. I should really just have the one line there. The conditional is 1 arrow to the conclusion. And so then construct your truth table, step 4, from statement in 3. And then do your thing we do here and see if the final answer column is all true, then you have proved it to be a valid argument. If there's one F along this final answer, then you throw it out and say it's not a valid, it's an invalid argument. All right, so here we go again. If you want to pause the video, this is when you do it. To practice this, we're going to go through the truth table idea on activity 2 and determine if this is valid or invalid. All right. So if you score 90% on the final exam, then, so I say if then you will get an A in the course. let's see what we got. If you score 90% on the exam, let's call that statement P, and then you will get an A for the core statement Q. So that's a if P, then Q, for sure. Then it goes on to say, premise 2, or the second sentence, you will not get an A for the course. Oh, that's not nice, is it? You will not get an A for the course, so our second line is not getting an A, that's statement Q, negating statement Q. Then it says the words therefore. Sometimes they make it more obvious. Actually, you see the line drawn here, but that's not always there. But the words therefore, or the 3 dots, you do not score 90% on the final exam. All right, so the therefore, under the line, the addition problem is you did not score 90%. That's negating P. So do we think that seems valid? I mean, it sounds like something we would say, like it seems reasonable if you talk that out to yourself. But we don't have that list going yet, so we're trying to do this like the old-fashioned way and prove it with the truth table. So we're just going with it and saying, how would I prove this? All right, so we got our argument written in symbolic form. We only have 2 players here, a P and a Q, so my truth table just needs the P and the Q, which is the 4 cases here. So case 1, 2, 3, 4, we're drawing our truth table. Either they're both true, true and false, false and true, or a false and a false. All right, so we're trying to prove this, and we say we write this sort of like a plus sign, so it'll be if P then Q, plus, or the and sign, not Q, and we need to put another parenthesis around, say, do all of that first, and then the conditional, the conclusion, you write your conditional sign, not P. All right, so that's what we have to do in our truth table. So we can do this. This is what we do, right? We've been doing this for a while in our lessons now, so let's do what we know here. Maybe this will be the last one I ask you to do like this. I think it is. So last truth table of our chapter, and then we'll move on to just the list so you don't have to go through all this each time. All right, so how do we do this? We're going to do this parenthesis first. So you always do the innermost parenthesis, which is a conditional if P then Q. So we look over here at P and Q, or you can copy them down if you feel it. But T and F is the broken promise rule with the conditional. Now the other ones are true. Then I will negate Q because I have trouble keeping that straight in my head if I don't write that down. Maybe you've noticed that too. So I will copy this down as the opposite of Q. And then the answer to it will be the and is the last part. So you know for and it takes 2 true. So not happening there or there. Let's see, here's a T and a T. That's the only time an and is true. So this is our answer to all of that string there, the parenthesis part. Now I will write down the negation of P because again I have trouble kind of keeping straight in my mind, so I like to have that visually where I can see the opposite of P. Then our final answer is the conditional here. We do the if a T to an F, you know the broken promise if you have true here leading to a false, but notice that does not happen. F to F, F and F, F to T is even fine, and T is fine. So the final answer to our truth table, all truths, that means yes, it's a valid argument. That's really what we're trying to do there. So that's how we prove it if needed. I'm going to pause the video here in a minute because this is a good place to kind of stop and say we'll come back in. Oh, and I'll let you do this too. It says in the next part, it says you can look these up in your book. So it's kind of good to look at our book sometimes and see. You can also read through the book and see some other good examples. But in the book, there's a list of some valid arguments. We've seen a couple of them already that we're going to mention here, and they have names, and then a couple that's invalid. So you can write those down. But I'm going to write it down in the next video as well and kind of use that for the rest of our lesson. All right, so I'll catch you back in a minute.